Go over first the equations of chapter 20, then we will do problems on it. So to start with the equations, in this chapter we will go over surface finish in machining, and mainly geometric factors will affect a lot the surface finish. So there are geometric factors constitute the machining parameters that will determine the surface geometry of a machined part. They include the type of machining operation, the cutting tool geometry, the node radius, mainly the node radius and feed. The surface geometry that would result from these factors is referred as the ideal or theoretical surface roughness. Okay, so we will learn together how to calculate the ideal value of the roughness. But since actually always we don't have things perfect, yani, we might have a deviation from this value. This is why we will see how we can account for the variation between actual and ideal roughness. Okay, so the effect of nose radius and feed can be combined together through this equation to find their effect on the roughness. So the roughness can be calculated as f square over 32 nr, where f represents the feed and nr is the nose radius of the tool. Now, as we said previously, in actual case, we might have deviation from this roughness. This is why we will see how to multiply this roughness by a certain parameter that will give us the actual roughness. In this equation, of course, and the node radius should be different than 0, because you can see here that we have an r in the denominator. So in case it tends to 0, or I will go to infinity. So this equation assumes that the nose radius is not 0, and that feed and nose radius will be the principal factors that will affect the geometry of the surface. Now, in order to account for tool wear and any other, if you want, unpredictable things, okay, we can come up with a certain factor that will give us the actual roughness compared to the ideal one. This can be done as we will see now. Okay, so we have several issues will affect the actual roughness of the surface. The main ones are the work material factors. So you know that achieving the ideal surface finish is not possible in most machining operation because of several factors, as for example, the built-up edge effects. We have the damage of the surface caused by chip formation. We have cracks, friction, etc. All these factors will affect in a bad way the formation, the finish of the surface. This is why in general, as we said, we can define an actual roughness that can be computed function of the ideal roughness times a certain factor. Now, this factor will be depending on the type of material that we are using, and also, so as you can see in the graph here, it will depend on the cutting speed and on the material used. So depending on the type of material, here you can see several curves. Each curve corresponds to a certain type of material: ductile metals, cast irons, free machining alloys. And for each type, you have the effect of the cutting speed on the ratio. So you can see that as the cutting speed will increase, then the ratio will decrease. And this means that the actual roughness, okay, will be much different compared to the theoretical one. Okay. Now, this is concerning the surface finish. Another important parameter is also in a machining operation is to optimize the cutting speed to use. So how we decide on the cutting speed to use, we have several criteria. First, we can select the cutting speed based on the maximum production rate, or we can select the cutting speed based on the minimum unit cost. So these two objectives in general are very important. We try to compromise between high production and minimum cost. Okay, so we will see now together how we can optimize the cutting speed for maximum production, and how we can optimize it for minimum cost, and then we can take a certain value of V that is compromising between the two, or if we care for one aspect more than the other, and sometimes we care for the rate of production more than the cost. This is why in this case we will just work on the first criteria. Or if we just want to minimize the cost, whatever is the rate of production, then we will use the second criteria. In general, we take a compromise between the two, and we try to find a value that will be acceptable for both. So first, now we will develop together how to optimize the cutting speed for maximum production and for minimum unit cost. In order to do this, we should understand what are the different steps in machining that will affect the time of production. Because if you want to maximize the production rate, you want to minimize the time required for unit product. Okay, and the time required for unit product can be divided into several steps. So you have first the part handling time, which is the time needed to load your part into the machine tool at the beginning of each production cycle. And also you should take into account the unloading time of the part at the end of the cycle. So these two times constitute the part handling time, TH. Now, also, any additional time required to reposition the tool for the start of the next cycle also should be included in this part. So if you want, it's just the time required to bring the setup ready to be used. In addition, all the time needed out of machining and tool change time. The second time is the machining time, which will be the time required to perform the operation, the machining operation. And finally, we have also to account for tool change time, because of course, in general, we don't change tool for each product, but we do it for a certain number of products, after a certain number of products. This is why to assess the tool change time per product, we calculate this time as the tool change per the number of the tool change time per the number of parts produced with this tool. Okay. Now, the total time then of operation can be written as T handling plus T machining plus the change tool time per unit product. And then what we will try to do in order to maximize the rate of production, we will try to minimize this total time. Okay. Now, in order to minimize it, we should find the functions. What are TH, TM, TT function of our variable? The main variable here is the cutting speed. Okay. So we will start first with the handling time. So in general, okay, the handling time is not affected by the speed of the machining operation, because as we said, the handling time is depending on the time needed to prepare the setup, and to put the to come up with the product near the machine near the machine to, and at the end to unload the part. So all of this will not be during the machining operation. This is why they will not be affected by the speed. So we can consider that this part is not function of the cutting speed. On the other hand, we have the machining time. The machining time we have already developed in previous chapters how to find. Okay, so now we will see that as cutting speed increase, as we have seen in previous chapter, the machining time will decrease, and also on the other hand, the tool change time will increase. Why? Why, if the cutting speed increases, the tool change time will also increase? What is the reason?
لأنه التول وير increases though.
Very good. Because when you have higher speed, you have the tool wear will increase, and therefore we need to change more frequently the tool. So these two parameters are affected by the cutting speed, the machining time and the tool change time, while TH is a constant relative to the cutting speed. No, it just depends on the time to put the setup and to unload the parts. Okay. So now, if you want to assess what is the function, TC function of V, we should express CM function of velocity. Also, we should try to express the tool change time function of the cutting speed. And then you know that to find an optimum, what I should do is I should derive. So once I get the equation of time, the total time function of V, I can derive this equation, okay, in order to find the optimal speed to use. Okay, so now we will see together the expression of our parameters. First, we have developed in previous chapters the cycle, the machining time. So the machining time for a certain operation is function of the length of the part, the work part diameter, and is inversely proportional to the feed and to the cutting speed. So you can see from this relation that as the cutting speed increases, the machining time will be reduced, okay, as we predicted before. Now, concerning the tool change time, okay, also we will see together how it can be related to the cutting speed. So now let us look just now at this figure and do some analysis. So first, you have all times are represented here, the three times. The part handling time, which is constant and independent of the cutting speed. We have the machining time that is decreasing with increasing speed, and we have the tool change time that will increase with the cutting speed. So now when you do the summation, since you have opposing effect of the cutting speed, so from one hand you have that the tool change time is increasing, and from the other hand with increased speed you have the machining time is decreasing. This is why when you do the summation of these three parameters, you will get a function with a certain optimum. This optimum, okay, will give you the minimum time required per work part, and therefore it will correspond to why we say Vmax. Vmax is defined as the velocity, the cutting speed giving the maximum production rate. So the max subscript is for maximum production rate. Okay. So this is how we can set the first objective. We can optimize the cutting speed in order to reach a maximum production rate in this way. Now, if you want to go to the analytical solution, if you want to do calculation, then as we said, we should express also the tool change time function of the velocity. Okay, and to do so, you know that the number of pieces per tool is function of the speed and can be written as shown. So you know that the tool life can be calculated using Taylor equation. Okay, and we if we know what is the number of pieces we can produce during the tool lifetime, then we can say that we can relate NP and T through the following equation, that the number of pieces produced is equal to the tool life over the machining time per part. And therefore, this will allow us to find the expression of NP, which is the number of pieces, function of the cutting speed. Why? Because you know that the tool life can be related to the cutting speed through the Taylor equation. Who remembers what is the Taylor equation? What was the Taylor equation? What was the relation? You have the tool life, okay, times V, which is the cutting speed to the power n, equals to a constant. Exactly. Okay. So V V times T to the power n equals to a constant. And then from the Taylor relation, we can find what is the expression of, we can replace T, okay, by its expression. Okay. So you have V times T to the power n equal to constant C. So you can write that T to the power n is equal to C over V. And then you can deduce that T can be written as C over V to the power 1 over n. Okay? So we can replace in this equation, we can replace the tool life by C to the power 1 over n over V to the power 1 over n. Okay? And also for the machining time, we have seen together the expression of the machining time. The machining time is pi dl over fv. Okay, so now if you replace t by its expression function of v, and if you replace tm by its expression function of v, you will have the following. You have c to the power 1 over n over v to the power 1 over n, which is the tool life that we got from Taylor equation, over the machining time. So it's times fv, it is times the feed times the cutting speed over pi dl. And therefore, if you simplify, here you have v, and here v to the power 1 over n. So in total, it's v to the power 1 over n minus 1. Your final equation for the number of parts that will be produced during one lifetime, okay, is equal to f, which is the feed rate, times the constant of Taylor to the power 1 over n, over pi dl times v to the power 1 over n minus 1. Now, if we replace back into our equation of total time, so as we said, T handling is constant, and the T machining is inversely proportional to the cutting speed. Now here, by replacing T total, which is the tool change time, over NP, because we got the NP function of the cutting speed, okay, then we can obtain the cutting speed function of the velocity. And you know that in order to minimize the total time, we obtain the expression of the total time of operation function of the cutting speed. So to minimize the total time of operation to produce one part, we should derive it with respect to v. So just all you have to do is to derive dt total by dv, and you set it equal to 0. This will give you the optimal velocity. In general, when we do the derivative, we can have a maximum or a minimum, but here you can verify that it is a minimum by doing the second derivative. So you are just responsible of the final result. Just I gave you this to understand how we got it. But of course, these equations can be helpful for you in problems. You can use them. For example, if they ask you for NP, you can find it using this relation. So now when you derive this equation with respect to time, you will get what is the velocity which will maximize the production. And when you set dt by dv equal to 0, you will get the expression of the velocity for maximum production. As you can see, it will be function of the Taylor constant. It will be function of the tool change time and of the parameter n in the Taylor equation. Okay. So now, once we obtain the optimal velocity, we can calculate the corresponding tool life for maximum production rate, okay, by just replacing the velocity calculated into the equation. So this will give us the tool life for maximum production rate function of the tool change time. Okay. Now, we will perform the same analysis, but now to minimize the cost per unit product. Okay, so now the criteria is different, is to minimize the cost, but the analysis will be similar. So first we should determine what are the different factors contributing to the cost of operation. So of course, any operation will have a cost. So you have the handling part, because you have a certain time for handling, this requires a certain cost. The cost of part handling time is the cost of the operator, the cost of the time the operator will spend loading and unloading the part. And as we said previously, any other operation required to have the setup ready can be included in this part. Okay, so we can just multiply the handling time by the cost rate, which is in dollar per minute of operation. This will give us the cost of the part handling time. Now, concerning the machining time, of course, we have a cost for the machining time. So also, if they gave us the rate the cost rate, which is in dollar per unit time, or in any currency unit per unit time. We multiply it by the machining time to get the cost of machining. And of course, we should add the cost of tool change time, because each time we change the tool also, this will cost something. So we should multiply by the cost rate. Now, in addition to these three parameters, we have the tool cost. Yani, whenever you change the tool, not only you should take into account the cost of tool change time, but also the cost of the tool, which might be much more important. So now, concerning the tooling cost, we should pay attention. We are just calculating the tooling cost per unit product. Okay, this is why in order to find this parameter, we will define the cost of the tool by the if you want, by the number of cutting edges, because you know that some tools can be used. Yani, we can just do small rotation of the tool and use another edge. Okay, so this cost is the cost per cutting edge CT divided by the number of pieces machined with that cutting edge. So what we will do first, you have a tool that can have several edges that can work. Okay, so first you should take into account that this cost should be divided by the number of edges, and for each edge, you know how much number of parts we can produce with this cutting edge. So in total, the cost per unit product will be the total cost, if you want, total cost of the tool over the number of edges, and then we multiply, which is called CT, which is the cost per cutting edge. Okay, and then we should multiply, we should divide this by the number of pieces that can be produced by one cutting edge. So this CT should be then divided by the number of pieces we can produce with this cutting edge. Okay, so as we said, concerning CT, in order to calculate it, it might be sometimes a little bit complex. So if we have several cutting edges, or if we have disposable inserts, okay, then we should divide the tool cost by this number of inserts. And also, as we have seen in the course material, the insert type will affect the number we will divide by the total cost of the tool. Because, for example, if you have triangular inserts that can be used only on one side, which is the case of positive rake tooling, then you will have 3 edges per insert. While if both sides of the insert can be used, which is the case of negative rake tooling, then for this triangular insert, you will have 6 edges per insert. So depending on the type of insert, when they provide you when they give you a problem, they will tell you what is the type of insert, and if it can be only used from one side or from 2 sides. Based on this, you will decide on the number you will divide by. So in case it is a triangular insert with only one side, okay, then you will divide PT by just 3. While if you can do operation on both sides, then you will divide PT by 6. And then after obtaining CT, you will, after obtaining this value PT over NG, you should also take into account in this cost the cost required for the grinding operation, because you know that sometimes, for example, an edge can be used even if it has a certain failure or a certain wear, you can repair this by grinding it. Okay, so sometimes also we can increase the number of times that we can use this edge by grinding the tool. This is why in this case, in case you are using grinding to use it again, we should take into account also the regrindable cost. Okay, so in case we have regrindable tooling, then as for example high-speed steel solid shank tools or brazed carbide tools, then the tool costs include purchase price plus cost to regrind the tool. And in this case, we should know what is the number of times we can regrind the tool. Okay, and therefore we can assess the value of CT. So CT will be the cost per tool life. PT will be the purchase price of the solid chain tool or the brazed insert, and NG will be the number of tool lives per tool, which is the number of times the tool can be ground before it can no longer be used. Okay, so sometimes, for example, we can use it 5 to 10 times for roughing tools and 10 to 20 times for finishing tools, which will reduce significantly the cost of operation. Okay, and TG represents the time needed to grind or regrind the tool, where CG will be the grinder's rate in dollar per minute. So this is in general how we can find the tool cost per unit operation. Now, once we determined all these parameters, all we have to do is to add them in order to find the total cost. So as we said, we have the handling cost, we have the machining cost, we have the tool change time cost, and we have also the tool cost. So all these parameters should be accounted for the total cost. Now, as we have previously done, the analysis done previously, the handling cost is independent of V, so this will be a constant. Since the machining time is function of V, so therefore also the cost will be, and it will be inversely proportional to V. Now, concerning these two parts, the two other parts, which are the cost of tool change and the tool cost per unit product, both are dependent on the velocity, because both we will divide both by NP, and NP is function of V as we have developed together. So just we have to replace NP by its value, function of the velocity. So we can see that we have opposed effect of velocity, because higher is the velocity, lower will be the machining cost. Okay, but also higher is the velocity, higher will be the tooling cost. Okay, this is why also in case of cost optimization, we will obtain the same analysis. So if we see the graph, we have the constant part is the part handling time cost. We have the tool cost and the cost of tool change time, both are increasing with the cutting speed, while the machining time cost is decreasing with the cutting speed. Therefore, when we perform the addition, we will have a certain optimum which correspond to the cutting speed, which will give us the minimum cost per work part. This is why we call it Vmin, because Vmin is referred to the speed for minimum cost, while Vmax represents the speed for maximum production rate. So as I told you before, sometimes we are interested in maximum production rate more, or sometimes we are more interested for the minimum cost, or we can compromise between the two. And for example, let's say you got that the minimum V for minimum cost, for example, let's say is 100 meter per second, for example. I'm giving any example, okay? And you got that Vmax is 200, for example, meter per second. Then you can say, I can take a compromise between the two, and I can take something in between, let's say 150, for example, okay? So it depends on your objective, on your target, to select the corresponding cutting speed. But if just your target is minimum cost, you will select this cutting speed. If your target is maximum production rate, you will select this one. And if you want to compromise between the two, you can take a value in the interval, and then you can be, if you want, close to both the minimum cost and maximum rate of production. Okay, any question concerning the explanation here? So now, also as we did previously, if you want to find analytically what is the velocity that will minimize the cost, all you have to do is to derive this expression. So this is a function of V. So if you derive it with respect to V, dc by dV is equal to 0, then you can get what is the velocity which will give me the minimum cost. And once I have the value of V minimum, I can determine the corresponding optimal tool change time. So I can find, based on this, the corresponding tool life function of the change time of the tool. Okay.
دكتور
So
بس عندي سؤال.
yes,
الكونستنت N و C بنجيبه من التابل بشابتر 19 ما هيك؟
yes, exactly. So if you want this chapter to solve for problems in this chapter, you need to use previous chapters. يعني the machining time was introduced بال 18. Taylor equation was introduced بال 19. So this chapter is combining several formulas in order to optimize the cutting speed. Okay. Okay. So I will open a new session to start with the problems.
اوكي دكتور.
Yeah.